Okay, so where we were last time is we're going back to rigid body kinetics. And rigid body kinetics, we deal with two different equations of motion. Two equations that relate the loads to the motion. The first one is Newton's second law, and that one says add up all the forces, the external forces acting on the body. That's equal to the mass of the chosen body times the acceleration of its center of mass. And then the second one, this is the new one, is the rotational version of Newton's second law. We didn't have anything like this it's not new like you saw it in Physics 1, but we didn't have anything like this in particle kinetics. And this is the one that says add up all the moments about A, the point A. That's equal to the mass moment of inertia about A times the angular acceleration, not angular velocity, and that's a vector. But there are restrictions on what A can be, unlike in statics. So A is either fixed in the inertial coordinate system or the center of mass. I might have done that in the opposite order before. But so now we only have two possibilities for where this about point is, unlike statics. The center of mass works for everything, but not everything has a fixed point. Not every body has a material point that's fixed as time goes by in the coordinate system. So if you think of like throwing a basketball through the air, there's no reason to think any point on the basketball is at rest over time compared to the coordinate system. One thing about this is we're doing this in 2 dimensions, so rigid body kinetics in 2D. And I mentioned before that in most things, going from 2D to 3D is just kind of a bookkeeping issue. You just have one more dimension, one more variable to keep track of. With rigid body kinetics, it's a little surprising to find out that it's fundamentally different. You can't approach it the same way. And I'll explain why when that comes up. But the way we're approaching this only works for 2D. What about 1D? There's no such thing as rigid bodies in 1D because you don't have any, you need extra dimensions for there to be sizes, for there to be orientation changes. So for this new rotational Newton's second law, we have to define the mass moment of inertia and the moment. The mass moment of inertia, I gave the definition of that. It's bigger if the mass is spread out farther. It's smaller if the mass is tight around the center of rotation. And so the mass moment of inertia about point A has an integral definition. It's the integral over the whole area of r squared dm, where r is the distance from the point A to that infinitesimal mass. And we're not going to use that integral definition very often. We're mainly going to use these formulas. And so I started this list of 4 shapes, 4 important simple shapes. But I only got through the first one. So now I'm going to just go through them all again. So formulas, they come from the integral definition. For 4 simple shapes. You don't have to use the integral definition very often, maybe never, because if you come up with a shape that you don't know the formula for, you just ask your smarter friend to derive a formula, and then you use the formula. Okay, so the first one is a slender rod. This is the only one I got to before. So we're assuming that the thickness, the width, is negligible. The coordinate system we're going to use for all these is centered at the center of mass. The origin's at the center of mass. And we'll call this X, Y, and Z. So with the about point at the origin, first about the x-axis, if you're assuming that that thickness is 0, then that's not a very good assumption if you're doing things rotating about the x-axis, but it would be 0 there. What you'd really want to use in that case, so if you have like a shape like this, a long cylinder, and you're dealing with rotations about the x-axis, you'd want to treat that as a disk. You'd get nonsense results by assuming that the thickness was 0. You'd use its actual radius and say it's a disk. But about the y-axis is the same as about the z-axis, and in both cases it's 1/12 times the mass times the length squared, and the length is this. Those should be parallel to the z-axis. So this is L. Okay, the next one is a rectangular plate. And we're going to make the assumption that it has a negligible thickness. So I'm going to call this a thin rectangular plate. And the dimensions, I'll call this B. And this C. And then the coordinate system, I'm going to call that X, that Y, and that Z. So for rotations about the x-axis, these distinctions we're going to use pretty often. So you're going to have to, little by little get used to thinking about how this thing is moving, what we're talking about when we talk about a rotation about x, a rotation about y, z. A rotation about x, this thing is thin, so you're imagining this is like throwing a, flicking a card or like throwing a Chinese throwing star, you know, like a blade. Okay. The other two are, so this is like a blade. The other two are like paddles, like a paddle wheel. Okay. Um, so about the x-axis, mass moment of inertia is 1/12 times the mass times the quantity b squared plus c squared. Notice that as the, like, let's say that you make that b get smaller and smaller, as it starts to get close to a negligible thickness, this thing gets close to like a rectangular stick, and that formula turns into that formula. Okay, so those agree with each other in that sense. Okay, now rotations about y. Now think of looking at the xz plane from the positive y-axis. What does this shape look like? It looks like a rectangular stick, right? We can't see the thickness into the page. And so we would expect this, so about the y-axis, we expect this to look like the formula for the slender rod. And so that's what we get. And what's the length that matters in that case? So we're going to have 1/12 times the mass times either b squared or c squared. C, exactly. And then about the z-axis, it's the same story, except this time the length that matters is b. So 1/12 mass times b squared. Yes, that's right. And then the third one is a thin disk. Okay, so this one, notice the question is always, so if you have a rectangular plate, are you talking about a rotation like a blade or a paddle? Okay, like the way it's rotating, if you put got your hand in its way, would it slice you or slap you? Okay, that's catchy. I'm going to use that in the future. Mental note. Okay, number 3 is a thin disk. Um, and I'll call that X, that Y, and that Z. About the Z axis, that's like if this disk is rolling. Okay, so any kind of rolling problem or a gear type problem, we're dealing with a rotation about Z. This is 1/2 m r squared. R is the radius of this disk. And the other two, about the x-axis or about the y-axis, if you think about those rotations, it's the same thing because of the axisymmetric, the fact that this disk is axisymmetric. And in that case, you get 1/4 mr squared. So it turns out it's actually a little easier to get a disk rotating like a paddle again than it is to get it rotating like a rolling wheel or like a blade. So notice, think, is it rolling or, paddle? And then the last one is a sphere. And we'll call the radius r again. And because every axis is the same for a sphere, and so all three of these, no matter how you orient the axes, are the same. And it's 2/5 mr squared. So with the sphere, it's easy. You don't have to, doesn't matter what the coordinate system, where it's pointed. It doesn't matter which axis you're rotating around. It's always the same. All right, so in which case is it easier to get the object rolling? A sphere or a disk that's like say rolling a penny down an incline or something, if the masses are the same? The sphere is easier than the disk. Does that make sense? Can you make sense out of why that is? So a sphere has, because it bulges out so if you're watching it roll from the side, now think of looking at it in the other plane. And that mass is distributed closer to the center because it bulges because of the round sides, you know what I mean? And so the more you have your mass distributed near the center, the smaller the mass moment of inertia is. They, yeah, they would have, so if they had the same mass and the same radius, the same moment applied to both of them would get the sphere moving faster. Yep. And then here's another sort of odd idea. This is all two-dimensional stuff. It might seem a little weird that we have to think about the distinction between a disk and a sphere, but the reason that we have to think about it is because of that fact that, the mass moment of inertia is determined by how the mass is distributed, how far it's distributed from the axis. And a sphere, even though this isn't happening in the plane that we're looking at, the sphere just does have more mass distributed close to the center. Okay. Any questions? Yes. Yes, yes. So just like the center of mass, you know, there's like a way to sum these up to make a complicated shape out of these simple shapes. Um, and in this case, it's even easier. You just add them all up. The one trick is you can't add them up until they are calculated about the same axis. Okay. So if you had, a shape that's like a sphere and a disk and I don't know. Yeah, skinny rod going through all of it. Um, and a rectangle. Um, and if you happen to want to calculate the mass moment of inertia about this axis, then you're in luck. You can just add up those three formulas. But if they're, okay, so if this is A, so for I sub A, just add the formulas. But that's a pretty special case. What about the case where you have a thin rectangular plate and another rectangular plate like that and um, let's say a circle removed here, you know, and you want to calculate this rotation about an axis like this. Well, then you're out of luck as far as just adding the formulas because the formula gives you the mass moment of inertia of this disk about its center of mass. Okay? The rectangle formulas give the mass moment of inertia about the center of mass of this one, somewhere like there, this one, somewhere like there. And um, all of those, you know, these centers of mass don't agree with the axis that we've chosen overall. So you can't just add the formulas. Because the axes are different. They are parallel though. So notice they are parallel. They go through different points. So the fix for that is the parallel axis theorem. So to find the mass moment of inertia about a point other than the center of mass, we'll use the parallel axis theorem. And what this says is, let's say we have this arbitrary object in 2D. And let's say that The center of mass is here. So let's say there's one axis here that we'll call C. And it goes through the center of mass. And then there's another axis that's parallel to C, but it doesn't go through the center of mass. I guess let's call that capital A. That's what I usually use for the axis or the about point in 2 dimensions. And let's say the distance between these two is D. Okay, so that distance D, where along those lines are we talking about that distance? Anywhere, exactly. These two lines are parallel, and that means that there's only one answer for D. If these two lines aren't parallel, the name of the parallel axis theorem gives you a hint that there's nothing you can do. Okay. So for this line C that's through the center of mass, the relationship we have is that the mass moment of inertia of this body about A is equal to the mass moment of inertia. Yeah, no, this is right. Mass moment of inertia about A is equal to the mass moment of inertia about C plus the mass of the object times the distance squared. Pretty awesome. So this M is the mass of the body. This D is the distance between the axes. So looking at this formula, where does the axis have to be for the mass moment of inertia to be small as possible? Center of mass, that's right. So you can't ever get smaller than that because M is positive, D squared is positive. And so any distance you move away from the center of mass for your axis is going to increase the mass moment of inertia. Okay, let's do an example. So let's say we have a rectangle in 2D. Let's say that this is H, this is W, and the mass is M. Let's choose a point A that's at the corner and calculate the mass moment of inertia about A. Okay, well, the formula gives us the mass moment of inertia about the center of mass. So mass moment of inertia about the center of mass is 1/12 times m times h squared plus w squared. And then the parallel axis theorem says the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass plus md squared. What's d squared in this case? So we're talking about this distance d. Half of each of those, right? So yeah, d squared is equal to w over 2 squared plus h over 2 squared. And so that's w squared plus h squared over 4. And so the mass moment of inertia about A is equal to, so I'll write it as 1/12 m h squared. I'm just distributing this 1/12 m through the parentheses in the first formula, plus 1/12 m w squared, plus, so mass times this distance squared gives us 1/4 m h squared plus 1/4 m w squared. And the common denominator for all these is 12. So you can come up with, so 1/12 plus 3/12 is 4/12. And so the answer comes out to this simple formula that, you could use from now on as a formula on its own when your axis is at the corner of a rectangle. And this is equal to 1/3 mass times the quantity h squared plus w squared. And so now, your smartest friend used the integral formula to give you this to represent the mass moment of inertia about the center of mass. And now, you don't have to call your smartest friend. He's probably got a lot of stuff going on. Your slightly dumber friend than that, but still pretty smart, use the formula, that first formula with the parallel axis theorem, to give you a new formula that now you can use forever. Okay. Any questions about that? I want to say one more thing. The thin requirements of these. When does it matter that, so on all of these except the sphere, we have these requirements, slender rod, thin plate, thin disc. When do those matter? They always matter for the rod. The rectangular plate the thinness only matters when you're rotating this like a paddle. Okay. If you're rotating this like a blade, it doesn't matter how thick into the page that is. So what do I want to say here? So if you're rotating it like a blade, that can be any thickness. If you're rotating it like a paddle, we're assuming that it's thin. And it works the same with the disk. If it's rolling, a thin disk rolls, the mass moment of inertia of a rolling thin disk follows the same formula as a long cylinder. Okay. The only time that it matters is when it's rotating like a paddle. So rolling can be any thickness. Paddle has to be a thin disk. Any questions about that? Yeah. Mm-hmm. Yeah, so if you, since for something rolling, like think of a disk when it's rolling. That formula for the rolling disk works for any thickness. So if you're talking about a rod, even if it's slender, but you're talking about it rolling about that x-axis, then just treat it as a disk. Okay. All right, the last thing, I'm not going to spend a lot of time on this, but I have to define a moment, and then once we do that, we're ready to go with with the rotational Newton's second law. So I can do this in 5 minutes. So the moment and of a force about a point the definition of this, you have some arbitrary body, and you have a force applied at some location. So let's say this is the force F applied at this point that I'm going to call P. And let's say this is the about point. Then define this new vector rho that goes from the about point to where the force is applied. That's the rho vector, Greek letter rho. Then the moment about A produced by that force F is equal to the rho vector crossed with F, where rho is a vector from the about point to the point where the force is applied. Another way you can think of that then is that mathematically the rho vector is equal to the coordinates of P minus the coordinates of A. When I do these, what I like to do for bookkeeping as much as anything else is set up a, rotational Newton's second law says you're going to add up all the moments applied by all the forces about your point A. So always set up a table with rows representing individual loads and the columns with places for that row vector, the force vector, and the moment vector. So like row, force, moment. And then it's really nice if you make a mistake and you can go back and you have all your old data sitting there, you know exactly where it is. It's easy to calculate the moment. You never get the order wrong or anything. So let's say that we have some force. This is just an example. I'm just making up these. Say that we have a force F. So we have a row for that. And we have a force R. And we have a couple that I'm going to call just M. Okay. So let's say from whatever about point we've chosen, the row vector to this force F is 0, 2, 1. The force vector is 0, 6,500, 0. Now the moment is the cross product of these two in this order. So you just get negative 6,500, 0, 0. Let's say this R vector has a, or this force R has a row vector of 1, 0, 0. The force is 0, 0, negative 9,000. And so the moment is 0, positive 9,000, 0. And then if this M is just a couple, we're not worried about either of these two things. We don't care about that. Couples don't produce any force, you know, because they're equal and opposite forces. So we can just write this in as whatever it is, you know, 0, 0, 5,000 or whatever. This wouldn't be a two-dimensional problem because we have non-zero values for all these. But the key thing is now, so first, having it formatted this way made it easy to calculate the moment without messing anything up. You know. The second thing is now sitting here in one space, you have all the force vectors that you're going to add up. So the entire left side of Newton's second law is right here. You're just adding up this vector plus this, plus, you know, keep going down. And for rotational Newton's second law, everything's right here, the left side of the equation. So this plus this plus this. And then in both cases, all you have to worry about is the mass times acceleration part. Yes? So it's the acceleration? It's angular acceleration. So no. Often we're going to want to calculate that, but we'll start doing example problems on Wednesday. We'll get into that. How many people have taken a class where you spent at least like a week or two doing angular accelerations? Would have been physics 1, kind of iffy. Okay, well, maybe I'll talk about that a little too. All right, see you Wednesday.